Apart from very regular structures that crystals can take, there are also these irregular shapes that somewhat remind me of dendritic structures in slate, or the shapes that form when you electrodeposit copper. And there's a funny but not very fast algorithm to simulate those structures, and it's called Diffusion Limited Aggregation, or DLA. So here's how it works. You start off with a seed point, with a static point here, so this point is not allowed to move. And you add to it one moving point, which starts a certain distance away from our seed point. And in each simulation step, our moving point is allowed just to move a tiny step into a randomly chosen direction. And after we move the point from this position to this position, and this is just a randomly chosen direction, after we move the point, we check if there is any static point within a given distance around that point. And if there's no static point close by, the point moves again choosing a random direction. So after a few iteration steps, and you can see by randomly choosing the direction, this point does not take the straightest path, we end up with a position where we actually find a static point within the vicinity of our moving point. And after we found a static point close by, the moving point turns into a static point as well, remains there fixed, and another moving point is born, again at a certain distance away from the static points, and again allowed to move freely and randomly. And this is the whole algorithm. This is everything that's needed to form those intricate structures. However, this algorithm is quite slow because you're adding one point at a time and the points have to wander around randomly and have to, by accident, get close to the static points. So are there techniques to accelerate that? Well, here are two ideas how to. On the one hand, when you look at this grown structure here, which we've grown according to the algorithm we just talked about, if a point wanders away too far from the bounding sphere, in our 2D case a bounding circle, so if the point wanders away too far from it, it's going to take quite time to come back to the area where it's actually interesting to have a moving point. So what we can do is, we can check if the moving point wanders away too far from our static points, and if it does, just move it back closer to our static points. Another idea is to have multiple points that can wander around simultaneously, in order to increase the chances of one of them sticking to the static points. Also, the number of moving points should increase with the size of the static point's bounding sphere, so that if our structure grows over time, we have more points the bigger it gets as the volume and the area of the bounding sphere increases, so we need more points to increase, or at least have the hit rate constant. Well, that is it for theory. Let's dive into Houdini and build the thing. In Houdini, the first thing I'm going to drop down, as always, is a GeoNode, dive in there and delete the file. I'll start by adding a single seed point using the add sop, and just at the center of it add one point. Now we need two groups, one for the static points and one for the moving points. Let's create them using Houdini H16's new grouping nodes. Just a standard group node. And the first group node is going to take care of putting this point that we just created, the center here. Let's increase the point size a bit. Let's put that point into the static group by going here, naming the group static. It should be a point group. And by enabling the base group, we just tell the group sub that the points feeding in here will be in that group. So highlight it, middle mouse button on it, and we see we have one point in the group static. Perfect. Let's create the moving group. Let's call this one move. Should be a point group as well. And by unchecking the base group, we can see that now we have 0 points in the move group and 1 point in the static group, just exactly as we want it. Now we can already drop down a solver, and in there we'll set up the simulation. So let's dive in there. And the first thing we want to do is spawn some moving points. So let's drop down a point wrangle, while previous frame in here, and let's take care of spawning moving points. First I'm going to declare some variables. I would like to be able to adjust the step length, that is how far my individual moving points can move per step. So by doing this, I'm just going to create a float slider for the step length, and in our case let's set that to 0.01. Now I need two vectors, min and max, and I need those in order to get the bounding box minimum and maximum, and I want to get the bounding box of all my points that are in the point group static. I want to get that by get point BB box, working on the 0 input slot, and I want to only regard points that are in the group static, and my minimum should be written into my vector min, and the maximum into the vector max. Now I'm gonna get the bounding box center. I could either use the get point BB box center, or I can just calculate the center. In our case, I'll just calculate it by defining a vector BB center, and I'm gonna calculate it by adding my minimum and my maximum vector together and dividing them by 2. Now, as you might remember, instead of a bounding box, I'd rather have a bounding sphere. So I have a center now. What I need is the radius. So let's calculate that. Bounding box radius equals the distance of my bounding box center and my maximum value. And in order to have a bit of room for my particles to move when they are spawned, I want to add some padding, and in our case let's add 2 times the step length. Now I want to define an integer that tells me how much moving points I already have in my simulation. So let's do that by finding an integer called number moving, and that is the number of points in the group move, and we work on a 0 input slot like so. So this expression tells me how many points there are in the point group move coming in through our first input slot. This is the input slot 0. Now let's define a number how many points should be moving. Let's call it target num for short, and it should be an integer. And I'm going to use the formula to calculate the area of a sphere. So by having my bounding sphere radius, I can calculate its area. And the formula for that is 4 times r squared times pi. So it's 4 times r squared times pi. That's 3.14592, something like that. And let's multiply that by a factor that tells us how many points should be there per area. So let's, in my case, multiply it by 4,000. So again, what we did here is we specified how many points there should be per area of my bounding sphere. So as my simulation grows, I will get more moving points in my simulation to accommodate for a growing structure and our growing volume. Now we want to check if our number moving, that's the points that are currently allowed to move or currently moving points in my simulation, is smaller than the target number. And if so, we'd like to spawn points in our simulation. So let's use a loop here. And we want to run this only as many times as the difference between our target number and our currently moving number. So in here we get the difference between our currently moving points in the simulation and the target number, so how many points there should be moving in the simulation. And we run the loop this amount of times in order to spawn new points. Let's first create a new point position. And this point position should lie on a sphere that has the same center as our bounding box and has a radius of the bounding box radius that we calculated. So we randomly need to get a position on that sphere. And there's a nifty technique for that. So let's define a vector. Let's call it npos for new position. And we need to get this position on the sphere with the center of BB center and with the radius of BB rad. So let's take the bounding box center and add to it. Sample sphere uniform generates a position on a sphere, and it takes as an input a vector of 3 values ranging between 0 and 1. So in order to generate this vector, and we just want to randomly choose a vector, let's use the nRandom function. And the nRandom function is a better pseudo-random number generator than the rand function, for example, which kind of gets important when you're doing simulations with that amount of particles that we do here, because when using a pseudo-random number generator like rand, you would see some patterns evolving there. So nRandom is a better random generator. Let's use that one. And we would like to normalize this. Like so. So now we have kind of a unit sphere. That means a sphere with a radius of 1 and its center on the BB center here. So let's multiply this by the radius that we'd like to. Like so, and we should be good. Let's check. Okay, let's save this and talk about what we did here. So this expression just generates a random position on a sphere, or within a sphere, that is. By normalizing it, we take care of the position always lying exactly on the sphere's surface and not within the sphere. By multiplying it with the bounding box radius, we take care of scaling that sphere, and by adding this vector here to the bounding box center, we just move that sphere to the bounding box position. So we generated a random position here. Now let's create a new point. So we just add a point here in the geometry stream at the position we just generated. Now let's set its groups accordingly. So this should be moving, so it should be in the group move, and it should not be in the group static. like so. Okay, let's check. Okay, we see we spawned a few points here. Perfect. Let's hit play. Nothing happens. That's good. Okay, dive into the solver again. Let's drop down another point wrangle. Oh, and by the way, we have to take care that this only runs once and not over all the points. So let's set this to detail only once and hook it up to the next point wrangle here. And within this point wrangle, we will take care of checking if there are any static points close by to the moving points, or to each individual moving point, that is. So in order to do that, let's create some variables here. For example, I need the maximum distance that I want to search for static points within. So let's say float. Let's call this max dist. Like this, and let's set this to 0.01. Also, what I'd like to introduce here in order to generate visually more interesting results, it can be interesting to give each particle a given stick probability. So each particle sticks only with a given probability and not all the time. So let's define that. Like this. And also let's define our step length. That's the amount each particle is allowed to move. Like so. Let's set our stick probability to 1 for now, and our step length to the same as the maximum distance. Like this. Now, as I did previously, I need to calculate my bounding box center for the static points, so let's just go in here and copy those lines. Paste them here. So here I get my bounding box, calculated center, and the radius of the bounding sphere. Now that we have done that, let's search for close points, for points that are within a given distance from our moving points, by using the nearPoint function. And we want to check for the nearest point on our 0 input slot. That is in the group static, and it should be close to our current position, and it should be within maximum distance. So this is trying to find the closest point in the point group static to our current point's position. Okay, let's check if we found something. So if near point is bigger than -1, because if it doesn't find anything, it'll return -1. So if it's not -1. And now I want to roll the dice and see if the point actually is allowed to stick here. So the stick probability comes in here. So let's check if a random number is smaller than our stick probability, then we can stick the point. So in order to stick that point, let's set its point group to static. And let's set its point group move to 0. So it's not allowed to move anymore. Okay, what if we didn't find anything nearby, or if the stick probability failed? Let's account for that. So if neither the stick probability was met nor anything was nearby, let's check if the point may have wandered off too far by checking the distance. And I'm going to use the distance squared function here. If the distance between the bounding box center or the bounding sphere center and our current point position is bigger than the bounding box radius squared, and I have to square it because this returns my squared distance, then we want to do something. And the reason I'm using the squared distance here is it is way faster to calculate than the standard distance, because I don't have to calculate the root. And as I can compensate for that by just checking against the squared radius here, this will yield faster execution times. So if the particle veered off too far, let's again take this line here and calculate a new position on the bounding sphere, or very close to the bounding sphere, and set our current point position to that generated position. That should be it. See? Okie doke, what do we have here? Oh yeah, maybe I should have defined those vectors first. Like so. And also this is called stick prob and not stick probability. Also in here, of course, I need my current point number in order to address the point. Like so. Okie doke. So this checks if any point is within the vicinity of static points. Now the final thing we need to do is move all the points in the move group around randomly. So let's drop down a final point wrangle. Wire this up so we have those 3 point triangles in a row, highlight it, and in here, let's generate a random vector. Again, using the inRandom pseudo-random generator, and let's multiply this by 2, and then subtract 1 from it. And what I do here is I basically just remap this vector, which goes from 0, 0, 0 to 1, 1, 1, into a space of -1, -1, -1 to 1, 1, 1. Now I'm going to look up my step length again. Again, set that to 0.01. And now we can add those two factors to a current point's position. So current position plus equals step, that is our random direction, times step length. That should be it. Okay, let's go up one level, highlight this and let it run. Okay, and we can see this gets big and it looks like a sphere. That is because we're displaying both points here, move and static. So let's get rid of the moving points and let's only see the static points by using a blast stop here, setting it to points, and let's blast away the move group. Let's run this. Okay, this does not really seem to work. Okay, let's check what's happening here in the solver. To me, it looks like we're not taking into account the groups actually, because we're currently moving each point regardless of their group. So what we need to do in order to account for the groups is in our last wrangle, let's just set the group to move. So this only takes into account all the points that are in the move group. Reset this and try running it again. Looking better. That kind of slowly evolves here. So let's increase our solver substeps here to, say, 32 substeps. And you can see a shape evolving, already starts to form those dendritic-like structures, but you can also see this thing kind of gets slow. And I really haven't found a way around this yet, so if any one of you has a better implementation technique for that, any ideas of speeding this up, please let me know, please hit me up. Highly interested in how you can actually get this thing to run faster. Until then, I think I'll just have to live with the slow simulation times. But I think we can add one thing to be able to artistically control this thing a bit better. And what I would like to do is add a volume here where I store a velocity vector that I will add to those small random steps that my moving points are allowed to make. So let's create a volume here first. Let's make it a bit bigger, let's say 6 by 6 by 6, increase its resolution a tiny bit, and append a volume bob. Also, before diving into the volume bob, let's make sure this volume is a vector volume and let's call it vel. Okay, middle mouse button on it, it's good. Okay, into the volume bob, let's drop down a bind export first, and we want to export vel, and we want to export a vector. Let's get rid of that here, and drop down our much beloved curl noise. So we wire up the position to P, and let's promote all the important parameters by middle mouse clicking on the slots and going to promote parameter. So we'll be later able to dial in the settings from outside of this VOP. Okay, let's wire up the output to our bind export here and head up one level. Let's just drop down a volume slice here to visualize what we've done. Okay, and maybe a volume trail, just to visualize the curl that we generated. Like so. Let's take this volume and wire it into the solver. And into the solver it comes here through the input 2, and we want to use it when we move the points actually here. So let's read out its current value by using a volume sample vector. So let's call it vector vel equals volume sample vector. And we'd like to sample the volume coming in through slot 2. We start counting from 0, so that's 1 here. We want to sample the first primitive, that's 0. And we want to sample it our current position. And after we sample this value, let's just add it to our vector that we calculated by multiplying step by step length here. So let's add it, plus vel. And I think currently, yeah, we can see here, those points already jumped a bit. Currently, our values stored in here are a bit too big. So let's go in here and drop down a multiply. and promote this parameter as well. And let's multiply this by, say, 0.01. That's equal to our step length, so might be a nice idea. Okay, let's highlight the blast stop again and let this run. Let's stop this here and maybe scale down the point size a bit. We can see here now we are attenuating the structures that form by this curl noise. So whatever you write into this volume here, or however you generate that, you can use that to drive the behavior of that simulation. And also what might be a good idea is to actually drop down a file cache after the blast, so we can actually write out those points here. And this expression here takes care of writing a file cache out into the same folder that my hip file resides, and it's going to create a new subfolder called geo, and then write out a bgeo sequence containing all the simulation data here. And in order for that to work, you just have to click on Save to Disk. After I run my simulation, I can either load it in directly from this pathway generated here, or I can load another simulation by just clicking here and select the according files. So I ran already 2 simulations here. Let's just take the first one here and load that up. Check load from disk and highlight the file cache, and you see it's a slightly different simulation that I ran here, and I ran it to actually 252 frames, I think, so that is longer than the current timeline. So how would I go about rendering this? Well, there are 2 techniques, and depending on which render engine you use, I prefer the one or the other. If you stay in standard Mantra, one thing you can just do is add a point triangle to our simulated point cloud here and just give it a p-scale value. So float called p-scale, and let's set it to something along the lines of our step length, so 0.01 here. Highlight this, and that's all you need to render out points in Mantra. Dive up 1 level and control click on our environment light here, and again load an environment map up in here. For example, this one, make sure you uncheck show sequence as one entry and just choose the corresponding HDR file here. Also, I want to control click on my camera symbol here to add a camera at the position where my viewport is currently, and I want to lock this camera with my viewport, so now I can move it around while moving my viewport. Also, what I'd like to do when rendering out stuff like this is add a background grid. So dropping down a grid here, just quickly dive in here, set this to be an XY plane like so, and let's just zero out our camera. So my grid looks directly into the camera, and by pressing space and 2 I can see a top view of my scene here, and I'll just take my grid and move it back quite a bit, let's say to -20. Space and 1 over the viewport gives me back my perspective viewport. Let's select my camera 1, and now I can wire up this grid to my camera so it always stays at the same position relative to the camera, except for it just made this jump, and that's because I did not check keep position when parenting. So let's undo this and check keep position when parenting first, and then parent this, like so. Now let's only scale this along its x-axis and the y-axis so it fills the frame, and now when I move my camera around, I can see my background grid follows, like so. Now let's pin my OBJ level here, and by pressing Ctrl T I can open another tab here, and let's use the output context here and drop down a Mantra node to configure our rendering. And when rendering out this stuff, I usually stick to the physically based rendering, and also I increase the diffuse limit in order to get some global illumination in here. And I think we can dial down reflect and refract limits here. Maybe let's increase the diffuse limit a bit. Say 8 bounces. Now I'm going to go to render view and hit render. And you can see my point size might have been a bit too big. So let's dive into our geo and let's decrease it a bit. That is due to the fact that I think the simulation that I loaded into the file cache here used a bit smaller scale than what I set up here. So I have to set my p-scale, and of course I have to call it p-scale and not p-scale. Like so. Yeah, and maybe the original value was good. Like this. And what I'm going to do now is tweak my light in here a bit, so increase the light intensity to, say, 2, so it gets a bit brighter, or maybe even 3. And also what I'd like to do is adjust some materials. So again, let's go to this tab and open up the material dialog in this case, and let's drop down. There are 2 basic shaders that I use when working quickly. One is the classic shader, and the other one is the principled shader, depending on what you like better. In this case, let's use the principled shader for the backdrop, so let's just use a dark gray background color. Yeah, let's leave it like that for now. And the classic shader will be my main shader for here. So let's make this a bit brighter and also give it a bit of subsurface scattering. And let's assign those materials on the geo node here where my simulation ran. Let's assign the classic shader, and for the backdrop, let's assign the principled shader, like so. And you can see here, due to the subsurface scattering, this takes a while to clear. So I'm just gonna click in here and see how that clears. And you might notice that in H16, the default behavior of the buckets changed. So when I release the mouse button, they are all over the place again. So by right-clicking in here and checking sticky priority, I can just leave them where I clicked them. Go back to the material tab and maybe disable the subsurface scattering, because that takes too long time, in my opinion. Now, if I want to set up depth of field, let's just go back to the camera here and stop this preview rendering and look at the scene from above by pressing space 2 again. So when I highlight my camera, I can press Z over the viewport and I get this gizmo, which is useful for setting the focus point and also depth of field. So this square box here tells Houdini where to put the focus point, and those two arrows indicate where the frame is actually in focus. Let's go back to the render view, render again. And we see that still everything is pretty sharp, pretty in focus. So let's check with the output context and the mantra node. And of course we need to check enable depth of field here. So now I'm getting these blurred depth of field effects where my object is out of focus. Although this looks promising already, and although it's highly tweakable when using mantra, you see rendering here takes a while. So here is how I would shade the scene using Redshift. So let's cancel that here, go back to our OBJ level here, hit space and 1 so I get my perspective viewport again, and let's get rid of those material assignments here, because I'm going to assign Redshift materials to those objects later. And also let's delete this environment light, because Redshift comes with its own light. So after you installed Redshift, you usually find it here, and if it's not there, just hit the plus, and in the shelves menu, just check that you have the Redshift shelf activated. So I'm going to drop down an Ares light dome first. That is the environment light that we're going to use. And in here, in the shader tab, I'm going to load in my HDR. Again, make sure show sequence as one entry is unchecked. Select the right HDR. And I want to increase the intensity, the brightness. So I'm going to use an intensity multiplier of 2. And let's go in the output context. Let's delete this mantra node here and drop down a Redshift. Or even better, let's just use this Redshift symbol here. And this will automatically drop down two things. A Redshift IPR, which is used to drive the interactive preview rendering, and the Redshift drop, which is there to configure Redshift. Let's just go into the IPR and uncheck override IPR camera resolution. I want to render in full resolution. And in the Redshift tab, let's go to global illumination and set the primary GI engine to brute force, secondary GI engine to brute force. This makes sure that global illumination is calculated properly in my IPR, because this is the only engine that my IPR can take into account, the brute force GI engine. So let's try and hit IPR. And my Redshift IPR pops open and I see a pretty white rendering. And this is white because background is pretty bright. So let's go in here and decrease the light intensity again and hit IPR again. And you can see, well, nothing basically. We can see just we are looking at this non-shaded background plane here without all those points. That is because Redshift currently cannot render those points as spheres. We have to take care of the instancing ourselves. So let's do that by dropping down an instance node here, which is a Houdini standard function. And on this instance node, I'm gonna attach Redshift data by clicking on the Redshift object parameters. So I can adjust the rendering parameters for this object in here. And what I want to do is instance a sphere. So let's create a sphere and dive in there. And in order to be able to render a sphere in Redshift, this has to be a polygon. So let's either check polygon or polygon mesh. Let's just use a polygon here, and this coarse subdivision will do for us. And then in the instance, dive in there and import our points that we want to instance the sphere on by dropping down an object merge. And we want to merge all those points that came in from our geosub, from the file cache, and I think from the point wrangle one. Let me just check one more time. Yeah, this is the last sub. It's always a good idea to attach a null to it. Let's call this out, so it's clear where the data goes out. And in our instance, let's just point it to that out node here, so we're sure. Okay, we can disable the visibility of our geo, and we can disable the visibility of our sphere. In our instance sub, in the instance tab, let's select the sphere as the object to instance on all those points. And I'm going to check full point instancing. So this should take into account the p-scale value on the points as well. As you can see here, the sphere gets scaled down and copied onto the points. And in contrast to using the copy sub for this, you can see my viewport stays fast. And also this is extremely efficient to render. So on our instance, let's again check with the Redshift OBJ tag under the instancing tab, instancing using Redshift instances. Perfect. Okay, let's try hitting IPR again. And we now see our point cloud rendered as spheres. So let's adjust some quick materials. Let's stop the rendering here. And I think this is going to change, but currently the Redshift materials only reside in shops still. So the new material context of H16 has not been taken into account yet. I think it's only a question of time, but for now I'm going to adjust materials in the shop context by dropping down a Redshift network node, and then everything is going to happen in this Redshift network node. And the most basic material you can create is just by dropping down a RS material node here, and let's choose the out color and pipe that into the surface output. And then in here in this node, I can adjust my materials pretty similar to what the classic shader or the principal shader offer me. In this case, I'm just going to go with a preset. The paper preset worked pretty nicely for the spheres. And let's go up one level, and let's call this one paper, and create another Redshift network, dive in there, again, drop down a Redshift material, wire the out color to the surface, and in this case, let's just adjust this manually by dialing down the reflection to 0, increasing the diffuse roughness to something like, say, 0.3, and choosing a dark gray as my main background color. Again, dive up one level, call this BG for background, and let's go to my OBJs and assign the background material to my grid here. So it's in the shop context and called BG, and the instances should get my paper material, again coming from the shop context here. So hit render again. Okay, that looks promising. Now let's take care of that depth of field by going into the camera and attaching camera parameters from Redshift here. And in the Redshift camera tag, under the depth of field settings, let's enable the depth of field, and let's check use Houdini camera focus f-stop. That means Redshift will evaluate the depth of field values and settings that the standard Houdini camera has. Let's render this. And we can see now we get this nice bokeh effect here and here in the front. What you could also do is uncheck use Houdini camera focus and f-stop, and in order for the IPR window to permanently stay on top, let's right click in here and say always on top. So I can dial in those values now and see if decreasing or increasing the focus distance changes anything. Maybe a bit too far away. Okay, something like this. We can see the corners of our background grid coming in here, so let's increase its size here, like so. And again in the camera, the circle of confusion radius drives how strong the depth of field is, so let's dial this down to say maybe 0.4 or even 0.2, and we dialed in our depth of field directly in Redshift now. So as you can see, a really quick engine, really fast engine, also a really versatile engine that runs on your GPU. So you need to have a powerful GPU or multiple GPUs to run it, but it's very efficient and it's extremely quick. And also it's, as I mentioned, very versatile, so you can import point data into your shading networks and use those for shading purposes, for example. So that was just a very quick intro to rendering in Mantra versus rendering in Redshift. I hope you had fun with generating this diffusion limited aggregation patterns. If you have a technique to speed up the whole setup, please let me know. I'd be highly interested in this. And also, if you create any artwork using this, just send us a link. We're always intrigued to see what you guys come up with. And it's cheers and goodbye.